Let's say a capacitor is connected to a voltage source, but there's a switch involved. So when the switch is open, current can't flow. What will the potentials of the different parts of the wire be when the switch is open? So if I call the negative terminal 0 volts, then we're going to have 10 volts up here. And the very tip of the switch would also be at 10 volts. However, point B is going to be at 0 volts. So the capacitor is uncharged. And there will be no delta V across the capacitor at this time. Why? Because charges need a complete circuit in order to be pushed onto the capacitor plates. With that in mind, point A would also be at 0 volts at this time. And this means that Q is 0. What if the switch is suddenly closed? We would expect a rearrangement of charges here to happen very quickly. Charges will want to reach the other side, and at first there will be a whole lot of surface area that they can pile onto. Once the charges pile on, we said that the capacitor would take on the same potential difference as the battery, and it would acquire a charge Q, which was given by the capacitance times the delta V of the capacitor. It is now charged. But how long does this process really take? Well, if there's not much resistance in the wires, then it can happen very, very quickly. Nearly instantaneously. What about the potentials around the circuit after it's been closed? What would those values become? Well, B would still be at 0 volts, but A will have changed from 0 volts to 10 volts now. And the positive plate of the capacitor would take on 10 volts. The negative plate would remain at 0 volts. What we're going to do next is we're going to introduce a resistor into the circuit and create what's called an RC circuit. RC circuits have both a resistor and a capacitor, as shown below. Let's assume that before the switch is closed, the charge on the plates is 0. And we'll go around the circuit and mark the potential values in this case. I'll put 0 volts on the negative plate. We'll have plus 10 volts above the positive plate. The tip of our switch is going to be at 10 volts. B will remain at 0 volts because it's in contact with the negative terminal. The delta V across our capacitor is going to be 0 because it isn't charged yet, which makes A at a potential of 0 volts. What about across the resistor? Well, if no current is flowing through the resistor, then there's no potential difference across it. So this point will be at 0 volts as well. What happens when the switch is closed? Charges will pile onto the plates, but because of the resistor, the current flow is going to be less than it would have been up here in this case. In this case, there's no real resistance mentioned in the circuit to oppose current flow or to slow it down at all. So we're going to expect the charges to be able to pile onto the plates very quickly because the current can be really huge. Down here, the current is going to be limited by the resistor. And so it's going to take time for the charges to build up. Eventually, though, They will build up. This section is all about understanding how current changes with time in RC circuits and how potential values in the circuit change with time as well. On this page, you can make several predictions about what you think different circuit quantities are doing as time goes on. For example, what is the current like in the resistor as a function of time? What is the charge on the capacitor like as a function of time? How about the delta V of the resistor and the delta V of the capacitor? We can even go as far as to put a subscript of R to represent the potential difference across the resistor. And we can put a subscript of C to represent the potential difference across the capacitor. Go ahead and make your predictions, and then I'll give my answers. All right, so when the switch is open, we know that current is not flowing because there's not a complete circuit. But what happens once that switch is closed? Does the current instantaneously jump up to a high value, or does it build up slowly with time? That's a tough question. Maybe we should start with the capacitor. How much charge is on the capacitor at the beginning, just as the switch has been closed? We know that there's no charge on the capacitor before the switch is closed. But what about when it is closed? At that very instant that it touches, does charge all of a sudden appear on the plates? Or does charge take time to build up? What's your guess? Well, the answer is charge takes time to build up on a capacitor. It's going to start off at 0. And there is going to be a maximum amount that the capacitor can hold. It's called Q max. And Q max will be given by the capacitance times the maximum voltage. Now, the way that it gets up to that level is by reaching a sort of asymptote or plateau. It approaches the upper limit of Q max without ever touching it, and it creates an asymptote throughout time. As we can see, eventually the plates become crowded with charge, and there's only so much that the capacitor can hold. Once it comes close to that limit of the maximum charge, current ceases to flow. And so for the current, what happens is it starts up high at a value which we could call I max. And it's actually going to decrease from there toward a limit of 0. So the idea is that when the switch is closed, the plates are wide open. Charges can flow very easily onto them. Let's draw it out in several pictures. There's the instant that the switch is closed. After some time, our circuit will be in a new state. And then there's what we call the long time state. This is after the switch has been closed for a very long period. Now let's put our resistor in here as well. That's important to slowing down the current. When the capacitor is uncharged, current will flow very strongly onto those plates. And in the same way that positive charge is attracted to the positive plate, we'd find that negative charge is attracted to the negative plate. But that means that positive charge is flowing away from that negative plate. So at a time when there's no charge on the plates, it's almost as if the capacitor isn't there. Current will flow as normal, as it would if just the resistor was in the circuit. Now, after some time has passed, there will be some charge piled onto these plates. Not the maximum amount, but just some. What this will do is it'll slow down the current. And once we've reached the long time state, after the switch has been closed for a long period, the plates will have acquired nearly their maximum amount of charge. And at this time, the current will slow to approximately 0. And interestingly, when this happens and current ceases, it doesn't matter whether the resistor is there or not at that point. And it's as if the capacitor were the only element in the circuit. Let's see how the potential differences across the resistor and capacitor change with time. When the switch is first closed, the capacitor isn't charged at all. It's got 0 volts across it. So we'll start here. There is, however, a maximum voltage that it can approach as time goes on. It's called Vmax. Then the maximum potential difference will equal the voltage across the battery. But what about the resistor? At the start of the clock, current is flowing quite strongly. And whenever current flows across a resistor, there must be a potential difference across that resistor causing it to flow. So the resistor voltage actually starts up high. But over time, current slows down. And according to Ohm's law, the voltage across the resistor will decay with time in the same way that the current is decaying with time. One last thing we can do with our diagram here is to label what the potential values are like at different points. So this would be an interesting point. So would this, and here at the negative terminal as well. At the instant that the switch closes, we're going to have 10 volts on our positive plate, of course, 0 volts at our negative plate. But what is this midpoint voltage going to be? Will it be closer to 0 or closer to 10? Well, we need current to flow through that resistor. We also need the delta V across the capacitor to be 0. We're going to have V max, the maximum possible voltage across the resistor at the start. And down here, our voltage across the capacitor is 0. This means that at this point, we need 0 volts. Why? because we have to have a current through that resistor, so we have to have a potential difference across it. We need to have no potential difference across our capacitor, though. Now remember, current can flow through the conducting wire very easily. If it's an ideal wire, then current can flow effortlessly. But the resistor does require a potential difference. Then let's look at the long time state. We're at 10 volts here in the positive terminal of the battery, 0 volts here. What will the potential in that middle section be now? Well, at this time, we need a big difference across our capacitor. The capacitor is going to have V max on it. So, we also have no current flowing. So at this time, the potential at that point will become 10 volts. When we're in between these extreme states, what we may have is 10 and perhaps 5 and 0.